A perfect dome has stood in Rome for 1,900 years. Modern concrete decays in decades, yet this ancient masterpiece remains flawless. By the end of this journey, you will know the precise Roman engineering secret that defied the ravages of time. We will uncover why a giant hole at its peak makes it stronger, and how the very rain that falls through it performs invisible repairs. What does this ancient structure suggest about our own modern ideas of permanence? It sits in the heart of Rome, not as a ruin but as a living building, surrounded by the skeletal remains of its own era. This is the Pantheon, originally commissioned by Marcus Agrippa around 27 BC as a temple to all gods. The structure we see today was completely rebuilt by Emperor Hadrian around 126 AD. Its journey did not end with the fall of Rome. In the year 609, it was consecrated as a church, an act of preservation that saved it from the fate of so many other ancient monuments. Its very name, Pantheon, means all gods, a purpose it has outlived in the most profound way. But its true claim to fame is not its history alone, it is an architectural rebellion. For nearly 2 millennia, it has held the record for the world's largest unreinforced concrete dome. No steel beams, no internal skeleton, just a single, breathtaking shell of Roman concrete, spanning an interior space of perfect harmony. While the Colosseum crumbles and the Roman Forum whispers of past glory through broken columns, the Pantheon stands complete, its massive bronze doors still swinging on original hinges, its marble floor still trodden by millions. This perfect preservation amidst a city of fragments is the quiet, monumental mystery. It should not be here, not in this condition. And so we must ask, what did the Romans know about concrete that we, for centuries, forgot? The secret is not in the grand design, but in the microscopic details of the material itself. Its scale is a silent declaration of ambition. Picture a sphere, a perfect geometric form, 142 feet in diameter. Now imagine that sphere placed inside the building, with the interior floor curving up to meet its base and the dome descending to complete its top. The distance from the floor directly beneath the oculus to the apex of that dome is also exactly 142 feet. This means the entire interior space of the Pantheon is a perfect sphere encased in a cylinder, a harmony of shapes that would feel mathematically serene even if you could not explain it. The dome itself is not a thin shell. It is a colossal mass of concrete, estimated to weigh over 5,000 tons. That is the weight of a modern naval destroyer suspended in mid-air with no visible means of support. And at the very top of this immense, heavy dome, the Romans cut a hole. They called it the oculus, the eye. It is not a small skylight. It is a gaping opening 27 feet across, wide enough to drive a city bus through. This presents the fundamental engineering paradox. In any structure, the apex is the point of greatest stress. If you built a stone arch and then removed the keystone at the very top, the entire arch would collapse instantly. By that logic, cutting a giant hole in the top of a 5,000-ton concrete dome should be an invitation for catastrophic failure. It should be the weakest point, the fatal flaw. Yet for 1,900 years, it has proven to be one of the dome's greatest sources of strength. The oculus is not an oversight, it is a masterstroke. It eliminates what engineers call the dead load, the sheer weight of material that would have been required to fill that central space. More crucially, it transforms the dome from a rigid, monolithic lid into a flexible, dynamic ring. When forces like wind or even minor ground movement act upon the Pantheon, the entire dome can flex and breathe slightly around that central void, distributing stress evenly throughout its curvature. The oculus acts as a built-in pressure release valve, preventing cracks from forming and propagating from the most critical point. It is the architectural equivalent of a martial artist rolling with a punch rather than standing rigid to absorb it. This giant hole makes the dome impossibly more resilient. The material holding this architectural defiance together is not what we think of as concrete today. It is something far more ancient and intelligent, a substance the Romans called opus cementitium. To understand its genius, we must first look at our own modern version. The concrete that builds our cities, our bridges, and our foundations is based on Portland cement, a recipe perfected in the 19th century. It is engineered for one primary goal: speed. It must set hard and fast, achieving tremendous compressive strength within days to keep pace with modern construction schedules. This speed comes at a hidden cost. The chemical process creates a rigid, brittle matrix. Under tension, it cracks easily, and to compensate for this brittleness, we embed steel rebar inside it, creating reinforced concrete. This works until it does not. Water and salt eventually seep through microscopic cracks, reaching the steel. The steel rusts, and as rust expands, it creates immense internal pressure, cracking the concrete from the inside out in a process called spalling. This is why so many modern concrete structures have a lifespan measured in decades, not millennia. They are fighting a slow, losing battle against their own internal chemistry. Now consider the Pantheon. Its dome has no steel skeleton. It has never needed one. Roman concrete, opus cementitium, was never designed for speed. It was designed for eternity. Its recipe was profoundly different, a mix of volcanic ash, lime, and chunks of rock aggregate, all combined with seawater. While our concrete fights against the elements, Roman concrete was designed to collaborate with them. It did not merely resist time, it engaged in a conversation with it. So the pivotal question becomes starkly clear. What crucial ingredient or process did the Roman builders understand? A secret that allowed their structures to grow stronger with age, that we somehow misplaced for over 1,000 years. The answer lies not in a single component, but in a chemical reaction that only begins once the concrete is already set. The secret ingredient was not mined from a quarry, but fell from the sky. Near the Bay of Naples, in a region of fierce volcanic activity, Roman engineers discovered a peculiar, fine-grained ash. This material, scooped from the ground around the town of Pozzuoli, was called pozzolana. To the untrained eye, it was just gray dust, but to a Roman builder, it was the magical powder that could turn simple mortar into eternal stone. They did not understand the complex chemistry, but through centuries of trial and error, they mastered its behavior. They observed that structures built with this ash-lime mixture not only hardened underwater, but seemed to grow tougher with the passage of time. It became the non-negotiable foundation of their most ambitious projects, from the harbors at Caesarea to the aqueducts that fed Rome, and ultimately to the dome of the Pantheon. So what exactly happens when pozzolana meets lime and water? The process is a slow-burning chemical marvel, known today as the pozzolanic reaction. Modern concrete relies on inert aggregates like gravel and sand, which do little more than provide bulk and filler. They are locked in place by the cement paste, but they do not actively participate in strengthening the bond over time. Pozzolana is the opposite. It is a highly reactive silica glass born from the intense heat of a volcano. When mixed with slaked lime and water, a long-term transformation begins. The lime, or calcium hydroxide, slowly infiltrates the microscopic pores of the volcanic ash particles. Over months, years, and even centuries, it reacts with the silica to form new, interlocking crystals of calcium silicate hydrate. Think of modern concrete as a rigid cage holding static rocks. Now imagine Roman concrete as a living matrix, where the glue itself is continually weaving new, fibrous connections between the pieces of aggregate long after the pour has set. This ongoing reaction is the key to its self-healing nature. It fills any tiny cracks that form with fresh, strong crystals, essentially giving the concrete an immune system. The aggregate within the Pantheon's dome was not random rubble either. Roman builders were masterful strategists of weight and strength. As the dome rises, the mix changes. The thick base uses heavy, dense travertine stone. Higher up, lighter materials like porous tufa and even hollow terracotta pots are embedded into the concrete. And at the very top, surrounding the oculus, the aggregate is almost entirely pumice, a frothy, feather-light volcanic rock. This graded design lightens the load precisely where it matters most, at the summit, reducing the downward and outward thrust on the supporting walls. The dome is not a uniform monolith. It is a meticulously engineered gradient, a mountain of concrete that gets lighter as it reaches for the sky. But the true magic of pozzolana required one final, crucial partner to activate its full potential. The Romans did not use fresh water from a river to mix this concrete. They used water from the sea. Salt water was the final, brilliant catalyst. While modern engineers see seawater as a corrosive enemy, the Romans treated it as a vital component of their concrete recipe. This was not a matter of convenience, using what was nearby for harbor construction. It was a deliberate choice even for inland structures like the Pantheon. Recent scientific detective work has uncovered why. Teams of researchers, including geologists and materials scientists from institutions like the University of Utah, have been drilling tiny core samples from ancient Roman seawalls and piers. They placed these samples under powerful electron microscopes, looking not at the concrete's bulk but at its atomic architecture. What they found was astonishing. Embedded within the 2,000-year-old matrix were perfect, plate-like crystals of a rare mineral called aluminous tobamorite. This mineral does not exist in nature at the temperatures and pressures found in a concrete structure. It had to have grown there slowly over centuries, and the key ingredient for its formation was the chloride from the saltwater used in the original mix. Here is the elegant chemistry. The salt ions act as a persistent, slow-acting agent. They facilitate a long-term conversation between the lime and the volcanic ash, encouraging the formation of these incredibly strong, interlocking tobamorite crystals. Think of it like this: modern concrete sets like a rigid plaster cast, hard but brittle. Roman concrete, with its saltwater catalyst, sets like a bone. It begins strong, but then it continues a process of slow, intelligent mineralization, filling voids and knitting together a more resilient, flexible internal structure. The chloride does not corrode this system, it perfects it. This is the ultimate rebuttal to our assumptions. We spend billions trying to shield our concrete from water and salt, seeing them as destructive forces. The Romans invited them in as partners, understanding on an empirical level that these elements were not the problem, they were part of the solution. The Pantheon's dome, though built on land, benefits from this same pozzolanic chemistry, a legacy of the maritime concrete science the Romans mastered. But a material this intelligent raises another profound question. If Roman concrete gets stronger with age, why did the knowledge to make it simply vanish for over 1,000 years? This ability to grow stronger with time suggests an even more remarkable feature. What if the concrete was not just durable but actively regenerative? What if the Pantheon's dome possessed a kind of architectural metabolism? This is the self-healing hypothesis, and it moves from the realm of clever chemistry into something that feels almost biological. For decades, researchers theorized that the long-term pozzolanic reaction could fill microscopic gaps, but the mechanism remained elusive. How could a solid stone structure, set 2,000 years ago, still possess the capacity to repair itself? The answer was hiding in plain sight within the very fabric of the concrete, waiting for the right trigger. That trigger is rainwater, channeled directly into the heart of the dome by its most famous feature. Every time it rains in Rome, water pours through the 27-foot oculus and splashes onto the marble floor below, but a significant amount of that moisture does not stay on the surface. It gets absorbed. The concrete of the Pantheon is not a seamless, homogeneous block. Under a microscope, it reveals a carefully engineered heterogeneity. Mixed into the volcanic ash and aggregate are countless tiny, white inclusions. These are lime-classed, small, unreacted chunks of quicklime that were a standard part of the Roman mixing process. For years, these white specks were considered a flaw, evidence of imperfect mixing by ancient laborers. Modern concrete production goes to great lengths to ensure a perfectly uniform, smooth paste with no such lumps. We eliminated what we saw as an imperfection. The Romans, it turns out, were building in a secret repair system. Here is how it works. When rainwater seeps into a hairline crack within the dome, it eventually encounters one of these tiny, dormant lime clasts. The water reactivates the lime, dissolving it and creating a calcium-rich solution. This solution then flows along the crack. As it interacts with carbon dioxide in the air trapped within the concrete or with the existing volcanic ash, it precipitates out as new crystals of calcium carbonate. These crystals are essentially a form of natural limestone. They grow, interlock, and gradually fill the void, gluing the crack shut from the inside out. It is a slow, precise process of mineral regeneration. Think of it not as a structure cracking, but as a wound healing. The lime clasts act like microscopic scabs, a built-in repair kit distributed throughout the entire volume of the dome. The oculus, therefore, is not just a structural relief valve or a source of light. It is the dome's life support system, the delivery mechanism for the healing agent. Each rainstorm is not an assault on the ancient fabric, it is a maintenance session. The Romans, through empirical genius, created a material that leveraged the environment it was meant to withstand. They designed a dome that uses the very element that destroys modern buildings to perpetually restore itself. This turns our entire understanding of material decay on its head. We build structures to resist change, to remain static in a dynamic world. The Pantheon was built to participate in change, to engage in a slow, symbiotic dance with wind, water, and time. Its strength is not in defiance but in collaboration. This slow, intelligent chemistry demanded an equally patient construction method. You cannot rush a material designed for eternity. Building the Pantheon's dome was not a single, dramatic pour of concrete. It was a careful, deliberate ceremony, performed ring by ring over an entire construction season. Imagine the wooden scaffolding that must have filled the rotunda, a temporary forest of timber rising to the heavens. Upon this skeleton, carpenters built the intricate formwork, the curved wooden molds that would give the wet concrete its perfect spherical shape. But here is the critical detail. They did not fill this entire mold at once. That would have been a recipe for disaster. The weight of 5,000 tons of wet concrete, all setting at different rates, would have created unimaginable stresses, cracking the structure from within before it even dried. Instead, the Roman engineers worked in horizontal bands, like laying the rings of a colossal stone tree. They would mix a batch of their special pozzolana concrete and pour it into a segment of the formwork, perhaps just a few feet high, all the way around the circumference. Then they waited. For days or even weeks, they allowed that single ring to partially set and cure, to begin its long chemical conversation. Only when it had gained enough strength to support itself and the weight above would they build the formwork a little higher and pour the next ring. This incremental process was a masterclass in load management. Each new ring placed its weight not on fragile, fresh concrete, but on a settled, stable foundation. It allowed the entire dome to settle uniformly, distributing the immense gravitational forces evenly down into the supporting drum walls. The construction itself became a slow-motion simulation of the final load, a gentle breaking-in period for the stone. You can still see evidence of this technique today. Inside the dome, the surface is marked by 5 distinct recessed bands called step rings that circle the interior. These are not mere decoration. They likely correspond to the working seams between the major pouring stages, the permanent imprint of the builder's patient ring-by-ring approach. This layered method also allowed for the strategic change in aggregate we discussed earlier. As the workers moved upward with each new ring, they could easily alter the concrete recipe, switching from heavy travertine at the base to lightweight pumice at the summit. The process was a physical manifestation of their deep understanding. They were not just building a shape, they were growing a structure, coaxing it into existence with a rhythm that respected both the material's needs and the laws of physics. It was architecture as a slow, deliberate ritual where time was not an enemy to be conquered but a necessary ally. Look up inside the Pantheon, and the dome is not a smooth, blank ceiling. It is carved into a breathtaking geometric pattern of 140 square recesses, arranged in 5 concentric rings. These are the coffers, and their beauty is undeniable, giving the ceiling a sense of rhythmic, celestial order. But to dismiss them as mere decoration is to miss a profound engineering calculation. Each coffer represents a deliberate subtraction, a scoop of concrete removed from the massive dome. In total, the coffers eliminated hundreds of tons of dead weight from the structure. This was a masterful act of optimization. The builders understood that every ounce of material at the height of the dome multiplied the outward thrust on the supporting walls below. By carving these voids into the finished concrete, they achieved the structural equivalent of drilling holes in a steel beam to make it lighter while retaining its strength. The dome remained thick and robust at its critical stress points, but became elegantly skeletal where it could afford to be. This was weight saving on a monumental scale, executed with artistic precision. But the coffers served a second, equally vital function during construction. Laying out a perfect sphere in wet concrete, high atop scaffolding without modern lasers or GPS was a staggering challenge. The geometric grid of the coffers likely acted as a giant, three-dimensional blueprint. Builders could use the pattern as a guide to ensure the curvature of each successive ring was perfect, checking their work against the emerging template above them. Furthermore, the sharp edges of each sunken square helped to stiffen the remaining concrete, much like the corrugations in cardboard prevent it from bending easily. This creates a subtle ribbed effect across the inner surface, distributing stresses and resisting deformation. Finally, there is the psychological genius. The coffers draw the eye upward, shrinking in size as they approach the oculus, creating an optical illusion of even greater height. They transform a static stone ceiling into a dynamic ascent, a visual ladder leading the gaze inexorably toward the light of the sky. The coffers are where brutal engineering meets sublime art, where removing material made the structure stronger, and where a geometric grid became a pathway to the heavens. This harmony of form and function points to a deeper truth about Roman engineering. It was never just about solving a problem, it was about solving it with an elegance that resonated for millennia. So if the dome is a perfect sphere and the walls are a perfect cylinder, how did they ensure this entire colossal mass would not simply push its supports outward and collapse? The secret lies in what you cannot see, hidden within the very fabric of the walls that hold the sky in place. The true sophistication of the Pantheon's dome lies in its invisible recipe. Roman builders understood that a single, uniform mix of concrete would create a fatal flaw, placing unbearable stress on the supporting walls. Their solution was a masterstroke of material science, a gradient of strength and weight that changed with every foot of elevation. At the very base of the dome, where it meets the massive cylindrical drum, the concrete is a brute. It is packed with heavy, dense aggregate, primarily travertine limestone. This stone, quarried from nearby Tivoli, is incredibly strong in compression, perfect for anchoring the entire structure and bearing the immense downward thrust. Think of it as the foundation of a mountain where the deepest rock must support everything above it, but as the dome curves upward, the recipe transforms. The builders began to introduce lighter materials. Layers of porous volcanic rock, like tufa, were mixed into the concrete. tufa is full of tiny air pockets, making it significantly lighter than travertine while still providing substantial structural integrity. This was not a random substitution, it was a calculated reduction in dead load. And then, at the very summit surrounding the oculus, the concrete achieves an almost miraculous lightness. Here, the aggregate is almost entirely pumice. This is the frothy, glassy stone that floats on water, created when gassy lava cools rapidly. Using pumice at the apex was a breathtaking risk that paid off for millennia. It meant the highest, most critical point of the dome was also its lightest. This graded design accomplished two brilliant feats. First, it dramatically reduced the total weight of the dome, easing the outward push on the walls. Second, it shifted the structure's center of gravity lower, making the entire assembly more stable, like a weighted bottom on a child's toy. They were not just building with concrete, they were composing with it, writing a symphony where each note, from the deep bass of travertine to the airy treble of pumice, played its part in perfect harmony. This meticulous layering reveals a philosophy far beyond mere construction. It was an act of profound empathy for the materials themselves and the physical laws they obeyed. But such a carefully balanced masterpiece would be useless without a foundation capable of receiving its immense weight. A foundation that had to be as clever as the dome it supported. That immense weight, over 5,000 tons of concrete and stone, had to go somewhere. It presses down from the perfect sphere of the dome onto the circular drum of walls beneath it. From the outside, these walls appear as a solid, formidable cylinder of brick. But their true genius is hidden, a secret internal anatomy that turns brute mass into a manageable force. The drum is not a solid block, it is a carefully engineered skeleton. Its thickness is staggering, reaching up to 20 feet in places. Yet within that 20-foot depth, the Romans did not simply pour concrete. They constructed a latticework of brick arches embedded like ribs within the concrete core. These are called relieving arches. You cannot see them from inside or outside the finished building. They are entombed within the wall itself. Their purpose was pure structural logic. An arch, by its very shape, is a master at redirecting force. It takes the weight from above and channels it down along its curves, pushing outward at its base. But when you embed multiple arches side by side within a thick wall, something remarkable happens. The outward thrust of one arch is counterbalanced by the inward thrust of its neighbor. They essentially cancel each other out, leaving only a pure, vertical line of downward pressure. Think of it as a series of stone rivers within the wall, each guiding the dome's immense load straight down to the earth in a controlled, orderly procession. This hidden framework acts exactly like the steel skeleton inside a modern skyscraper, but crafted entirely from brick and mortar 2,000 years ago. Furthermore, the Romans incorporated strategic cavities and voids within the drum's mass. These were not mistakes, they were deliberate lightning chambers. By removing non-essential material, they reduced the overall weight of the drum itself, which in turn reduced the burden on its own foundations. More importantly, these voids provided flexibility. They allowed the entire massive structure to settle and shift minutely over centuries without developing catastrophic cracks. The wall could breathe. So the drum is far more than a simple support. It is an active participant in the dome's stability. It receives the chaotic, omnidirectional push of the curved dome, and through its internal archwork translates it into a calm, orderly descent. It is the silent mediator between the ambition of the heavens and the reality of the earth. That giant hole at the summit is the dome's most brilliant deception. In any arch, the central stone, the keystone, locks everything into place. It bears the greatest compressive force. For a dome, which is essentially a rotating arch, the apex is its keystone. To follow conventional logic, the Romans should have made that point the thickest, heaviest, and most fortified. Instead, they removed it entirely. By cutting the oculus, they eliminated the single most critical point of failure. There was no massive keystone to crack under its own unimaginable weight, no central hub where stress could concentrate and shatter the entire system. The oculus transformed the dome from a rigid lid into a flexible, continuous ring. Think of it not as a missing piece, but as a built-in release valve. When environmental forces like wind or thermal expansion push against the dome, the entire structure can flex minutely around that central void. The stress is distributed evenly throughout the curved shell, traveling down along infinite, imaginary arch lines that all lean against one another for mutual support. The opening forces the concrete to work in perfect, harmonious compression, the state in which it is strongest. It is an architectural paradox that makes perfect sense, a void that creates stability. But its genius extends far beyond the unseen physics. The oculus is the Pantheon soul, its connection to the living world. It is the building's only source of natural light. A single beam, sharp as a blade, slices through the dim interior, painting a brilliant circle on the floor and walls that marches slowly across the marble as the sun moves through the sky. This moving spotlight acts as a colossal sundial, marking the hours and seasons within the sacred space. On rainy days, it becomes a column of falling water, a dramatic cascade that drains through almost invisible holes in the floor, a reminder that this structure is in dialogue with the elements. And it breathes. The oculus acts as a giant chimney, allowing hot, stale air to rise and escape while drawing in cooler air from below. This natural ventilation prevents moisture buildup and keeps the interior atmosphere fresh, a simple yet effective climate control system engineered 2 millennia ago. So the oculus is far more than a skylight or a structural trick. It is the eye of the building, a purposeful opening that provides light, air, and a dynamic connection to the cosmos above. It turns an enclosed temple into a living observatory, proving that the Romans understood a profound truth. Sometimes the strongest form is the one that is open. Yet all this architectural brilliance, the graded dome and the hidden arches, would mean nothing without an anchor. The true foundation of the Pantheon's immortality lies not in the air but deep within the earth. While our eyes are drawn upward to the oculus and the coffers, the real hero of this story is completely invisible, buried beneath the marble floor. Before a single brick was laid for the walls, Roman engineers began with a radical act of excavation. They dug a vast circular trench following the exact footprint of the future rotunda. This was no shallow ditch. It plunged deep into the unstable alluvial soil of Rome, a ground notoriously prone to shifting and settling. Into this giant earthen ring, they began a meticulous, layered process. They did not simply dump loose rubble or pour a single slab. Instead, they constructed a massive artificial footing built up in deliberate strata. First, a layer of thick concrete made with the same pozzolana ash for strength. Then, a layer of compacted rubble and broken bricks. Then another layer of concrete and another of rubble. This sandwiching technique, known as opus cementitium, created a monolithic raft of incredible stability and distributed weight. Think of it not as a foundation, but as a man-made geological formation. They were essentially building their own bedrock, a circular plateau of engineered stone wide enough and deep enough to act as a perfect, unyielding table. This robust base performs one critical, silent function. It prevents differential settlement. In any large structure, if one corner or section sinks even slightly more than another, catastrophic cracks will race upward through the walls. The Pantheon's layered foundation ensures that the colossal weight from above, all 5,000 tons of it, presses down evenly across its entire surface. The load is dispersed so completely that the ground beneath it cannot react unevenly. It is the ultimate shock absorber, a buffer between the ambition of the building and the reality of the soft Roman earth. Modern engineers often focus on the visible marvel, the dome itself, but the Romans understood that eternal architecture is a conversation that begins in the dark. The Pantheon does not simply stand on the ground, it is rooted in a stone embrace of its own making. This hidden footing is the patient, uncelebrated reason the dome has not tilted, slumped, or split apart over 20 centuries. It is the steadfast whisper from below, answering every thrust from above with perfect, immovable calm. The Pantheon's enduring strength speaks to a deeper philosophy, a way of thinking about the world that has largely vanished from our modern construction sites. For the Romans, engineering was not merely a technical discipline, it was a branch of moral philosophy guided by principles articulated by the architect Vitruvius. He argued that every great structure must embody three inseparable qualities: fermitas, utilitas, and venustas. Fermitas is strength and durability, the physical integrity that allows a building to stand. Utilitas is utility and function, serving the needs of its users effectively. Venustas is beauty and delight, the aesthetic grace that elevates the spirit. The Pantheon is the ultimate expression of this triad. Its fermitas is the self-healing concrete and the hidden arches. Its utilitas is the oculus providing light and air, the vast open space for congregation. Its venustas is the breathtaking harmony of the sphere within a cylinder, the coffers drawing the eye heavenward. These were not separate checkboxes, but intertwined threads in a single vision. To compromise one was to fail at all three. This stands in stark contrast to much of modern engineering, where projects are often governed by a different, more urgent triad: speed, budget, and immediate function. We build for decades, they built for centuries. The Roman goal was eternitas, eternity. They envisioned their works as permanent gifts to the future, legacies in stone that would outlive empires. This long-term mindset fundamentally changed their calculus. They could invest years in constructing a single building, patiently layering rings of concrete season after season. They could source special materials from distant volcanoes, trusting that the extra effort and cost would pay dividends for 1,000 years. Their secret ingredient was not just pozzolana ash, it was patience. It was the willingness to let chemistry work on a geological timescale, to design structures that collaborated with time rather than fought against it. We see rain as a threat to concrete. They designed a dome that used it for repair. We see salt as a corrosive. They used it as a catalyst. This is more than a difference in recipe, it is a difference in perspective. The Roman engineer saw himself as a steward of permanence, building a dialogue between human ambition and the natural world. Our challenge today is not to rediscover a lost concrete formula, though that is fascinating science. The deeper challenge is to recover that lost mindset, to ask what we are building for and who we are building for. Are we constructing disposable shelters for our own generation, or are we crafting enduring gifts for generations we will never meet? The silent, perfect dome in Rome asks us that question every single day. The fall of Rome was more than a political collapse, it was a technological amnesia. As the empire fractured, the intricate supply chains that brought pozzolana ash from distant volcanoes to construction sites across the Mediterranean snapped. The specialized guilds of builders, the architecti who understood the precise ratios of lime, ash, and seawater, dispersed. Their empirical knowledge, never fully written down in a comprehensive manual, faded into folklore. In the centuries that followed, the recipe for true Roman concrete was not improved upon, it was utterly forgotten. The great structures it had built were seen not as products of a replicable science, but as miracles of a lost golden age, works of giants that could no longer be equaled. The Pantheon itself, consecrated as a church, was revered and maintained, but its material essence was a mystery. Medieval builders looked at its flawless surface and saw divine providence or superhuman effort, not a chemical process they could learn. They returned to simpler, more labor-intensive methods, stacking stone upon stone, relying on mass and geometry alone. The secret of the self-healing stone was buried as deeply as any Roman ruin. Centuries later, a new dawn of human ambition looked back to Rome for inspiration. the Renaissance was a rebirth of classical ideals in art, literature, and architecture. And no structure captivated the imagination of Renaissance architects more than the Pantheon. Its perfect proportions, its daring scale, its very existence as a complete ancient building made it the ultimate textbook. In Florence, a city brimming with wealth and civic pride, a monumental challenge arose. The unfinished Cathedral of Santa Maria del Fiore had a gaping hole in its roof where a dome was meant to go. The planned dome was wider than the Pantheons, and no one knew how to build it. The man who claimed he could was Filippo Brunelleschi, a goldsmith and clockmaker with no formal architectural training. His proposal was audacious. He would cap the cathedral with the largest dome built since antiquity, without using expensive wooden centering, the temporary internal scaffolding that was standard for arches. To win the commission, he famously stood an egg upright on a marble table by cracking its bottom, demonstrating that once the solution is seen, it seems simple. His real solution, however, was born from years of clandestine study. Brunelleschi traveled to Rome and spent years living among the ruins, meticulously measuring, sketching, and reverse engineering the Pantheon. He grasped its double shell design and its stepped rings of masonry. He understood the principle of the oculus as a compression ring, but he was missing the crucial ingredient literally. The chemical secret of pozzolana concrete was invisible to him. He could measure the form, but he could not reproduce the substance, so Brunelleschi did something brilliantly different. Since he could not use self-bonding concrete, he invented a new structural logic. His dome for the Florence Cathedral, completed in 1436, is a masterpiece of brick and stone, not of monolithic concrete. He built two thin, concentric shells with a hollow space between them, connected by a skeletal framework of ribs. This created a light, stiff structure, much like an eggshell. To counteract the outward thrust that his dome generated, he employed a series of massive stone and iron chains buried like giant hoops within the brickwork. These chains act as permanent tensile belts, cinching the dome together to prevent it from bursting outward. It is a work of staggering geometric and engineering genius, but it is a fundamentally different solution to the same problem. The Pantheon's dome is a single, homogeneous mass that gains strength from its internal chemistry and graded weight. Brunelleschi's dome is a complex lattice, held together by physical restraint and precise masonry. One collaborates with material science, the other masters structural force. This divergence proves a critical point. The Renaissance recovered the Roman ambition and aesthetic, but not their material alchemy. They could emulate the shape, but they could not resurrect the soul of the stone. Brunelleschi's triumph, while magnificent, underscored a permanent loss. The Florentine dome is a feat of construction, while the Roman dome remains a phenomenon of material. One is a brilliant answer to a geometric puzzle, the other is a conversation with time itself, a distinction written in every rain-washed surface of the ancient concrete. The Pantheon's secret remained locked in its stone for centuries, a silent testament to a forgotten craft. Then, in the 21st century, a new kind of explorer arrived. They came not with shovels and brushes, but with particle accelerators and electron microscopes. Their quest was not to unearth artifacts, but to decode the atomic architecture of Roman concrete itself. Leading this charge was a geologist named Marie Jackson. Her laboratory at the University of Utah became ground zero for a microscopic archaeological dig. The challenge was immense. You cannot simply take a sledgehammer to the Pantheon's dome. Instead, Jackson and her international team secured permission to extract tiny, pencil eraser-sized core samples from ancient Roman marine structures like the piers at the harbor of Caesarea. These 2,000-year-old concrete blocks, submerged in seawater since their construction, held the purest form of the recipe. The first breakthrough came from a tool of staggering power, the synchrotron. This is not a simple microscope, it is a stadium-sized ring that accelerates electrons to near light speed. As these electrons race around the ring, they emit incredibly intense, focused X-rays, a light billions of times brighter than the sun. By aiming this brilliant beam at a sliver of Roman concrete, scientists could perform a kind of high-definition chemical cartography. They could map, atom by atom, the precise arrangement of minerals within the sample without destroying it. What they saw was a crystalline wonderland. The synchrotron X-rays revealed the delicate, plate-like crystals of aluminous tobermorite, the rare mineral that acts as a reinforcing fiber within the concrete matrix. More importantly, they could see how these crystals were woven throughout the material, forming a resilient, interlocking network that grew stronger over centuries. This was the visual proof of the slow pozzolanic reaction in its final, perfected state, but the synchrotron showed the finished product. To understand how it got there, they needed to see the repair mechanism in action. This is where the scanning electron microscope entered the story. This instrument uses a focused beam of electrons to scan a sample surface, revealing details down to a nanometer, a billionth of a meter. Under this incredible magnification, the white lime clasts, long dismissed as flaws, were revealed to be something else entirely. They appeared as angular, unreacted islands floating in the concrete sea. The microscope showed that cracks propagating through the aged material would inevitably run into one of these clasts, and at the interface between the crack and the lime, researchers could see the newly precipitated crystals of calcium carbonate, the healed scar tissue of the concrete. They had caught the self-healing process in the act, frozen in time for 2 millennia. This was the eureka moment. The lime clasts were not mistakes, they were a deliberately engineered, distributed repair system. When water infiltrated a crack, it preferentially dissolved the highly reactive lime, creating a supersaturated solution that flowed into the fissure and crystallized, sealing it shut. The Romans had essentially embedded a powdered repair kit throughout their structures, a kit that remained chemically active for ages. Jackson's team, alongside researchers from around the world, began to reconstruct the full recipe. They confirmed the vital role of the volcanic ash, its specific silica and alumina content. They pinpointed how the salt from seawater acted as a catalyst, not a corrosive, facilitating the long-term growth of the strengthening tobermorite crystals. They quantified the ideal mixing ratios and the importance of the graded aggregate. For the first time since the fall of Rome, the empirical knowledge of the architecture was being translated into the precise language of modern materials science. The code was finally cracked. We now know with laboratory certainty what the Romans knew through observation and tradition. But this revelation was not an end point, it was a starting gun. If we can read the recipe, a tantalizing new question emerges: can we write it again? The cracked code now sits in modern laboratories, not as a historical curiosity, but as a blueprint for a more resilient future. Around the world, materials scientists are attempting the ultimate act of reverse engineering, mixing volcanic ash, lime, and seawater to create new concrete that behaves like the ancient kind. This is not about nostalgia, it is a pressing search for solutions to some of our most urgent problems. One of the most ambitious real-world trials is happening in the chilly waters of San Francisco Bay. Researchers from the University of California, Berkeley, have cast large concrete blocks using a modernized Roman recipe, rich in volcanic ash, and submerged them in the bay's saltwater. The goal is direct and profound: to monitor these blocks over years and decades, watching with modern instruments to see if they develop the same self-healing crystals and grow stronger with time, just as the Roman piers at Caesarea did. This is a long-term experiment on a Roman timescale, a patient bet that ancient wisdom can solve modern fragility. The potential benefits, if successful, are staggering. Consider our coastal infrastructure, the seawalls, breakwaters, and piers that protect our cities. These are frontline structures in a constant, losing war against saltwater corrosion. They are built with Portland cement concrete and steel rebar, a combination destined to spoil and decay, requiring costly, disruptive, and carbon-intensive repairs every few decades. Now imagine a marine concrete that does not fight the sea but learns from it. A concrete where the chloride ions in seawater are not enemies but partners in a long-term strengthening reaction. Structures made from such material would not just last longer, they could potentially maintain themselves, reducing the need for constant human intervention. The environmental implications are equally transformative. The production of Portland cement is one of the largest single industrial sources of carbon dioxide emissions on the planet, responsible for roughly 8% of global emissions. This comes from the immense heat required to cook limestone and from the chemical reaction itself. If we could build structures that last for centuries instead of decades, the need for constant demolition, reconstruction, and new cement production plummets. Durability becomes the ultimate form of sustainability. A seawall that stands for 1,000 years represents a massive reduction in its lifetime carbon footprint, locking away emissions that would have been repeated over and over. Furthermore, a self-healing concrete could revolutionize construction in places where repair is difficult or dangerous, like the foundations of offshore wind turbines, deep-sea oil rigs, or even radioactive waste containment facilities. The material would possess a kind of embedded resilience, a capacity to recover from the small, inevitable cracks that doom ordinary concrete. This is the grand promise emerging from the study of the Pantheon's dome, a future where our built environment is not a burden on the planet but a durable, intelligent partner. Yet, translating a 2,000-year-old recipe into a viable modern industry is a challenge of epic proportions, a clash between ancient patience and the relentless pace of the contemporary world. The Pantheon's genius extends beyond defying gravity to mastering the very atmosphere inside it. This is a building designed not just to stand but to breathe. Its environmental systems are a masterpiece of passive design, leveraging the structure's own form and material to create a stable, comfortable interior climate without any moving parts. This silent, constant regulation is another crucial, often overlooked layer of its longevity. Let us start with the most dramatic element, the rain. When a storm sweeps across Rome, water pours through the 27-foot oculus in a torrential column. Far from being a problem, this deluge is part of a meticulously planned hydrological system. The marble floor of the rotunda is not flat, it curves gently upward at the edges and slopes almost imperceptibly toward the center. Carved into that central marble are 22 nearly invisible holes, small drainage apertures. The rainwater that crashes onto the floor is immediately channeled toward these drains and carried away through ancient Roman pipes beneath the building. This rapid removal prevents pooling, eliminates standing moisture that could damage the precious marble or the subfloor, and maintains a dry interior surface for visitors. The system is so effective that the floor is often dry mere minutes after a downpour ends. But the oculus's role in climate control is far more comprehensive than just a dramatic drain. It is the building's primary source of ventilation. Hot, stale air naturally rises. In a sealed dome, that heat would be trapped, creating a stifling, humid environment perfect for fostering mold and accelerating decay. The oculus acts as a giant chimney, allowing that buoyant warm air to escape continuously. As it flows out the top, it draws in cooler, fresh air from the main entrance and the smaller niches below. This creates a gentle, constant convection current, a natural air conditioning system that has been running for 2 millennia. The building perpetually exhales its own breath, preventing the dank stagnation that plagues so many ancient structures. Then there is the matter of temperature itself. Step inside the Pantheon on a blistering Roman summer day. Outside, the sun beats down on the travertine and brick, and the city air shimmers with heat. But cross the threshold and you are met with a profound, enveloping coolness. This is not a coincidence, it is physics. The secret lies in the concept of thermal mass. The Pantheon's walls and dome are not just thick, they are monstrously massive. All that concrete and stone acts as a gigantic heat battery. During the cool night, the entire structure slowly releases any stored warmth and cools down. When the scorching sun rises, the exterior surface heats up, but that heat takes an extraordinarily long time to conduct through the 20-foot thick walls and into the interior space. By the time the outer layer is hot, the inner surface remains cool. The interior mass of the building simply absorbs the minimal heat that does penetrate, preventing the air temperature from spiking. The process reverses in winter. The thermal mass, having absorbed ambient warmth during the day, slowly radiates it back throughout the colder night, taking the edge off the chill. This creates a remarkably stable, temperate microclimate year-round, a sanctuary of consistency. This passive climate control is engineering of the highest order. It requires no energy, produces no waste, and has never needed a repair manual. By collaborating with fundamental principles of physics, hydrodynamics, and thermodynamics, the Roman architects built a system that maintains the building's integrity from the inside out. A stable, dry, temperate environment is a gentle one. It does not subject the materials to extreme cycles of expansion and contraction. It does not promote rot, and it does not encourage salt crystallization within the pores of the stone. In this way, the environmental design is not separate from the dome's longevity, it is integral to it. The Pantheon cares for itself, using the sun, the wind, and the rain not as adversaries, but as tools in an endless, elegant dance of preservation. Rome is a city built on a fault line, a fact its ancient architects knew all too well. The Italian peninsula is seismically restless, caught between the grinding collision of the African and Eurasian tectonic plates. Over the past 2,000 years, this geological tension has released its fury repeatedly. The historical record is a litany of violent shakes, major earthquakes that have flattened cities, toppled temples, and rewritten landscapes. In the year 444, a tremendous quake struck Rome, damaging the Colosseum's upper tiers and cracking the foundations of countless monuments. Another powerful tremor rocked the city in 847. Then, in 1349, one of the most destructive quakes in central Italy's history struck, leveling buildings across the region. Each of these events was a direct, violent test of the Pantheon's engineering, and each time the Great Dome stood, it did not emerge completely unscathed, but it survived structurally intact when so much else around it was reduced to rubble. Its endurance is not a matter of luck or divine favor. It is a direct result of the very properties we have just explored, working in perfect concert under the most extreme duress. Consider what happens during an earthquake. The ground does not simply move in one direction, it lurches, shakes, and rolls in complex waves. This subjects a building to multidirectional forces, pushing and pulling it from all sides. A rigid structure, like a thick wall of solid stone, cannot absorb this energy. It resists until it reaches its breaking point, and then it shatters. The Pantheon, however, was designed with a kind of intelligent flexibility. Its concrete, with its ongoing pozzolanic reaction and interlocking crystal structure, is not brittle. It possesses a degree of tensile strength and, more importantly, a capacity for micro-cracking without catastrophic failure. When seismic waves travel up through its foundations and into the drum, the hidden lattice of brick relieving arches within the walls allows the force to be redistributed and dissipated. The entire massive cylinder can sway ever so slightly as a unified, flexible unit. Then the force reaches the dome. Here, the giant oculus proves its worth once more. The open ring at the apex allows the dome to flex and deform minutely, like a diaphragm breathing under pressure. The stress is channeled around the continuous, curving shell, never finding a single, rigid point to concentrate its destructive power. The graded concrete, lighter at the top, reduces the inertial mass that the quake's energy tries to move. In essence, the building was designed to ride the wave, not to stand rigidly against it. After the shaking stops, the real test of longevity begins. Even the most flexible structure will develop hairline fractures under such strain. This is where the Pantheon's self-healing metabolism engages. The same microscopic cracks that would spell the beginning of the end for a modern concrete building become sites of regeneration here. Rainwater, channeled through the oculus and absorbed into the porous concrete, seeks out these new fissures. It finds the dormant lime clasts, dissolves them, and deposits new calcium carbonate crystals, slowly gluing the wounds shut from the inside. The earthquake becomes not just a survived event, but a trigger for the building's own repair cycle. This combination of flexibility and active healing is a 1-2 punch against seismic decay that no other ancient structure possessed in such a complete form. Look at the ruins that surround the Pantheon in the Roman Forum. Those temples and basilicas, many built of rigid travertine blocks or inferior concrete, could not flex. They fractured at their joints, their columns toppled, and once they fell, they stayed fallen. Their materials had no capacity for recovery. The Pantheon's survival is a quiet, monumental rebuttal to the idea that strength is only about brute mass and rigidity. True resilience, it demonstrates, is about collaboration with force, not defiance of it. The building bends so it does not break. It accepts small, manageable damage so it can avoid total collapse. And then, with patient chemical intelligence, it heals itself. This is why it still has its original bronze doors, its intact marble floor, its soaring, complete interior space. It weathered the earthquakes that history recorded, and doubtlessly countless smaller tremors that went unlogged. Each event left its invisible mark, a network of tiny fractures that were subsequently filled with new stone, making the fabric of the building slightly stronger, slightly more interlocked over the centuries. The dome does not just resist time and chaos, it metabolizes them. In a seismically active land, surrounded by the skeletal remains of its own era, the Pantheon stands not as a monument to static perfection, but as a testament to dynamic, living endurance. It asks us a profound question about our own modern structures, built in earthquake zones around the world. Are we designing them to merely survive the next big one, or are we building them to learn from it and to prepare for the one that will come 1,000 years from now? For centuries, the sheer impossibility of the Pantheon's dome bred explanations that lived outside the realm of engineering. When a structure defies all common understanding, people turn to magic and myth to fill the void of knowledge. One of the most persistent legends speaks to the fundamental question of its support. How, people whispered, could such a massive stone ceiling hang in the air? The story goes that Emperor Hadrian, desperate to ensure the dome's success, ordered his workers to pile the entire interior of the rotunda with loose earth, mixed with a fortune in gold coins. This earthen mountain was shaped into a perfect hemisphere, forming a giant mold upon which the concrete was slowly poured, ring by ring. Once the dome had fully set and cured, the emperor announced a spectacular reward. The people of Rome were invited to come and take the earth away and to keep any gold coins they found within it. A frantic, joyous excavation ensued, and as the last cartload of soil was hauled out the great doors, the dome was revealed, miraculously suspended above the empty space. It was a perfect tale, explaining the unexplainable with a narrative of imperial cunning and public treasure. While the method of using an earthen mound for support has historical precedent in other cultures, the golden incentive was pure folklore, a poetic answer to the engineering marvel that left observers speechless. Another legend, born from its transformation from a pagan temple to a Christian church, centers on the oculus itself. When Pope Boniface IV consecrated the building in the year 609, sanctifying it as the Church of St. Mary and the Martyrs, the story claims that the pagan demons inhabiting the old temple were violently expelled. As they fled the holy rites, they burst upward through the very center of the dome, tearing the giant hole as they escaped to the sky. This myth gave a divine origin to the oculus, framing it not as an architectural choice, but as a permanent scar of spiritual warfare, a sign of the building's purification. These stories are more than just charming fables. They are a vital part of the Pantheon's history because they record the human reaction to its presence. For over a millennium, with no understanding of pozzolanic reactions or graded aggregate, people could only interpret the dome as a supernatural phenomenon. The legends of the Golden Mound and the fleeing demons are testament to its awe-inspiring power. They mark the point where engineering achieved such perfection that it was indistinguishable from magic. The concrete reality, once uncovered by science, is in many ways more wondrous than the myths, but those old stories remind us of the profound mystery this building presented to every generation that stood beneath its impossible ceiling. The Pantheon was not an isolated miracle of Roman engineering. It was the crowning achievement of a civilization that had been experimenting with domes for centuries, pushing the boundaries of space and light. To truly appreciate its singularity, we must glance at its siblings, the other great vaulted spaces of Rome that used similar ideas but fell short of its perfect synthesis. Take the immense baths of Caracalla, completed around 217 AD. This was a sprawling leisure complex, a playground for the masses featuring vast halls, pools, and libraries. Its most famous surviving vault is not a true dome, but a towering cross vault covering the central frigidarium, the cold bath. Yet, the baths also contained smaller, genuine domes over the circular hot rooms, the caldaria. These domes were built with Roman concrete and used lightweight pumice aggregate at their apexes, just like the Pantheon. They even incorporated clerestory windows, smaller versions of the oculus concept, to let in light and steam escape. The techniques were there, the material science was understood, but the baths of Caracalla are a magnificent ruin today. Their domes collapsed long ago, leaving only fractured walls and fragmented arches. Why did they fail where the Pantheon endured? The answer lies in integration and support. The baths were a complex web of interconnected spaces, each vault pushing against another. When one section weakened or was damaged, the failure could cascade. More importantly, their foundations, while robust, may not have matched the Pantheon's deep, layered, and perfectly circular footing. They were grand applications of the technology, but not its ultimate, self-contained expression. Then there is the curious case of the Temple of Minerva Medica, built in the late 3rd or early 4th century AD. This structure is fascinating because it represents a bold, later evolution of the dome idea. It was not a temple, but likely a grand nymphaeum, a fountain house within an imperial garden. Its design was decagonal, 10-sided, and it featured a concrete dome that was not a solid mass, but a pioneering example of a ribbed dome. Large, arched windows were punched directly into the drum beneath the dome, making the upper structure appear almost to float on light. The builders used brick ribs to reinforce the concrete, a step toward the skeletal approach Brunelleschi would later perfect. It was lighter, more open, and architecturally daring. Yet today, the Temple of Minerva Medica stands as a haunting, roofless shell. Its dome collapsed in antiquity. The very innovations that made it feel so airy, the large windows and the ribbed design, may have created fatal points of weakness. The thrust from the dome was not contained by a continuous, massive drum like the Pantheons, but was channeled onto slender piers between the windows. Over time, that concentrated stress likely proved too much. These other domes teach us a vital lesson. The Romans possessed the ingredients for immortal architecture, but combining them into a flawless recipe was exceptionally rare. The Pantheon succeeded not because it used a secret unknown elsewhere, but because it brought every element to its logical, perfect conclusion. It had the ideal, simple form, a sphere within a cylinder. It had the deepest, most stable foundation. It used the graded concrete with flawless execution. It balanced the oculus not just for light, but as a structural keystone. and it was consecrated and maintained continuously, saving it from the stone robbers who plundered the baths and the temple for their brick and marble. The other domes show the experiments, the brilliant attempts, and the partial successes. The Pantheon alone shows the finished masterpiece, where every risk was calculated, every force was harmonized, and the conversation with time was designed to last forever. Its perfect form became a ghost that haunted architects for centuries. Long after the recipe for its concrete was forgotten, the Pantheon's silhouette remained the ultimate symbol of grandeur, harmony, and civic power. Its influence did not fade, it evolved, migrating from ancient Rome to become the blueprint for the modern world's most important spaces. When the founders of a new republic looked for an architectural language to express their ideals, they did not turn to the Gothic spires of monarchs or the wooden halls of colonial meeting houses. They looked directly to Rome and specifically to the Pantheon. The United States Capitol dome, completed in 1863 during the Civil War, is its most famous descendant. Architect Thomas U. Walter was explicitly inspired by the Pantheon's proportions and its majestic oculus, though in the Capitol, the oculus is enclosed by a monumental fresco called the Apotheoses of Washington. The form communicated stability, democracy, and a connection to Republican antiquity. Yet this dome, like so many others, is a shell of cast iron painted to look like stone, supported by a complex internal iron framework. It mimics the shape but replaces the monolithic, self-supporting mass with a lattice of industrial metal. It is a tribute to the idea, not a replication of the method. Across the Atlantic, another temple of knowledge paid homage. The Great Court of the British Museum, with its breathtaking glass and steel roof completed in the year 2000, seems a world away from Roman concrete. But at its heart lies the iconic reading room. This separate, domed structure within the museum, completed in 1857, is a direct and deliberate homage. Its vast cast-iron dome is almost identical in diameter to the Pantheons, and it uses a nearly identical pattern of coffers, those sunken square panels, to lighten its visual weight and draw the eye upward. For generations, scholars like Karl Marx and Virginia Woolf sat beneath this dome, surrounded by the collected knowledge of the world, in a space designed to evoke the serene order of the ancient original. From city halls and libraries to banks and universities, the neoclassical movement that swept Europe and America in the 18th and 19th centuries was in essence a love letter to Rome, with the Pantheon as its central text. Columns, porticos, and rotundas became shorthand for legitimacy, wisdom, and permanence. But this was a borrowed vocabulary. Architects could measure and reproduce the geometry, the ratios, the aesthetic effect. They could create spaces that felt eternal. What they could not do was rebuild the substance. They could not recreate the slow alchemy of pozzolana ash and seawater, the patient ring-by-ring construction, or the self-healing metabolism. For over 1,000 years, the soul of the Pantheon was missing. The buildings inspired by it were often beautiful, sometimes structurally ingenious in their own right, but they were wearing a mask. They achieved the look of eternity through careful maintenance, constant restoration, and eventually modern engineering materials like steel and reinforced concrete. The original, meanwhile, simply was eternal, requiring no such intervention. This is the poignant legacy of its influence. We have spent centuries copying its shadow while the substance remained a locked secret. We mastered its image long before we understood its essence. That deep material mystery is what makes the Pantheon, even today, truly irreplicable. You can build another dome of the same size, but you cannot build another dome that thinks, breathes, and heals like this one. Yet for all we have uncovered, the Pantheon guards final mysteries. We know the ingredients, but the exact recipe, the hands-on ritual of its creation, remains just out of reach. How did the Roman builders, without electric mixers or digital scales, achieve such a perfectly consistent blend of volcanic ash, lime, and aggregate, batch after massive batch? The mixing procedure itself is a lost art. Was it done in a giant trough by teams of laborers rhythmically turning the slurry with shovels? Was there a specific sequence for adding the seawater, a crucial step that could mean the difference between a strong mix and a failed one? We can guess, but we cannot say for certain. The workmanship is another enduring puzzle. Look at the interior surface of the dome, at those 140 coffers. Each one is a precise square recession, carved into setting concrete with flawless geometric alignment. They did this while suspended on wooden scaffolding by torchlight with simple plumb lines and string. The margin for error over such a vast curved surface was virtually zero. A single misaligned coffer would throw off the entire visual harmony, yet they achieved perfection. This speaks to a level of craft and spatial intuition that borders on the supernatural, a transmission of skill from master to apprentice that left no written manual. And what of the material itself? Our core samples and synchrotron scans have revealed the broad strokes of the concrete's composition, but the dome is a three-dimensional object poured in rings over many months. Are there microscopic variations in the mix from one side to the other, subtle adjustments the builders made in response to weather or material availability that we have not yet detected? Could there be local reinforcements, pockets of specially formulated concrete around the points of greatest stress, hidden in plain sight? Each unanswered question is a reminder that this is not a solved artifact. It is a living document, and we are still learning to read its finest print. The Pantheon, in its silent, enduring way, continues to challenge us. It offers its secrets slowly, one raindrop, one scan, one question at a time. The Pantheon's secret is not a single lost ingredient, but a complete philosophy cast in stone. It is the synergy of perfect volcanic ash and seawater, a chemistry that grows stronger with centuries. It is the self-healing lime clasts, a distributed repair kit waiting for the next rain. It is the graded dome, light as pumice at its summit and anchored by travertine at its base. It is the brilliant oculus, a void that gives it strength and a conduit for light, air, and healing water. It is the hidden arches within the drum and the deep, patient foundation beneath the floor. And above all, it is the mindset of the builders, their commitment to fermeters, utilitors, and venusters, strength, utility, and beauty, woven into one eternal purpose. They built not for the dedication ceremony, but for a future they would never see. In our modern world of planned obsolescence and carbon-intensive, disposable construction, the Pantheon stands as a silent, profound rebuke. It asks us what we are building for. Are we creating shelters for a generation or legacies for a millennium? Are we fighting against nature with brittle materials or learning to collaborate with its forces? This dome does not represent a technology we lost, but a perspective we misplaced. The next time you see a photograph of that perfect interior, remember you are not looking at a ruin. You are looking at a conversation, one that began 1,900 years ago between human genius and the elements, a conversation that is still ongoing, whispered in every falling raindrop and etched in every sunbeam that crosses its marble floor. That is the true secret of eternity. So the story does not end beneath this ancient dome. It continues with you. What other mysteries of the ancient world do you think hold secrets for our future? Is there a lost technology or forgotten wisdom you believe we are on the verge of rediscovering? Share your thoughts and speculations in the comments below. Your curiosity is what keeps these stories alive, and if you want to join us for more deep dives into the enigmas of history, be sure to subscribe. The Pantheon's final, resonant lesson is this: true resilience is not about rigid defiance. It is found in flexibility, in collaboration, in designing systems that welcome change as a partner. The greatest strength comes from working with nature, not against it. That is the whisper carried on 2,000 years of rain, a secret written in stone and sky, waiting for anyone who looks up and wonders.